Application, it's called oxygen-independent regulation of HIF-1α and ILC3s ameliorate the inflammation of C. rodentium-induced colitis. And it's presented by Ana Valle-Noguera de la Complutense de Madrid. No?
So my name is Ana Valle. I'll be presenting my work. It's called HIF-1α as a regulator of colitis, innate lymphoid cell type 3 during Citrobacter rodentium colitis. So as a brief introduction that has already been made by the previous talk, the ILC3s are tissue-resident cells that lack the expression of the TCR. They are classified now into 5 subtypes based on the development and the characteristics of these ILCs. They have different functions throughout the body, as the previous talk has mentioned. But we are going to focus on ILC3s that have the expression of the transcription factor ROR gamma T. So ILC3s are mainly found in the intestinal tract, and they have a function of against extracellular bacteria and fungi, mainly secreting interleukin-22 and interleukin-17. So one of the main characteristics of an infection is that you have tissue hypoxia. The main master cellular transcriptional regulator of hypoxia is HIF. HIF can be regulated in the immune system in 2 known ways. The classical, most studied one is by oxygen levels. When there is oxygen in the ambient, HIF gets ubiquitinated and degraded. When there is no oxygen, HIF gets stabilized by binding to HIF-1 beta, and it goes to the nucleus. So the other non-classical way is a transcriptional one. It's mainly induced by external signalings, such as cytokines, TCR, or TLRs, and does not depend on the oxygen levels. So our hypothesis is that HIF-1α is regulating the function of ILC3s and the secretion of the cytokines they exert through signaling through cytokines, pumps, or oxygen levels in a translational or post-translational or transcriptional way, or both. So the objective in this study is the in vivo study of HIF-1α in ILC3s in a mouse model of Citrobacter rodentium-induced colitis to ascertain the molecular regulation of cytokine secretion through HIF-1α in ILC3s. To do so, we have newly generated new transgenic mice by crossing mice that have HIF depleted in ROR gamma T cells. So ROR gamma T cells are not only ILC3s, but also some T cells. So we have crossed these mice with rag mice that lack T and B cells. So the resulting mice has HIF deleted only in ILC3s and does not have T or B cells that can interfere with the results. So we have also tested this deletion that is by qPCR, so to validate the mouse model. So the first thing we have done is to study in steady state these mice, as they are new and have not been studied. And the first thing we did was a UMAP study that we see the different subtypes of ILC3s. We do not see any difference between the wild type and the knockout mice. We also tested that they do not develop spontaneous colitis or have any affection on the histo score. And also, we tested the secretion of cytokines, and surprisingly, we saw that it's already affected in the steady state, the secretion of interleukin-22. So HIF-1α indeed does regulate the secretion of interleukin-22 in ILC3s. So, as per the model of infection, we use Citrobacter rodentium. We infect those mice orally with Citrobacter rodentium, and we monitorize them throughout the infection. Why we have decided to use this mouse model is because in the early phases of infection of Citrobacter rodentium, the ones that are fighting against the infection are ILC3s, mainly by secreting interleukin-22 and also interleukin-17. So it must be a good model. So as we have seen that these mice already have interleukin-22 higher levels than wild type, we were expecting them to perform better during the infection. However, when we infected them, we see that the survival is impaired, that they have greater weight loss, that they are more histologically damaged, they have more colony-forming units, and what we saw is that unexpectedly, yes, they do have more interleukin-22 in steady state. However, they are not able to upregulate this interleukin-22 secretion. On the other hand, the wild-type mice are able to do it. So that's why the results. So now that we have seen that, yes, HIF-1α does indeed regulate the interleukin-22 secretion in ILC3s, we wonder the molecular mechanism was through cytokines, PAMs, oxygen level, post-translational, transcriptional. So we have focused mainly on cytokines and PAMs because we have seen that actually HIF is transcriptionally upregulated during the infection in colon and also in sorted ILC3s. So it must be a transcriptional regulation of HIF. So to do so, we made colonic explant. We cultured them with different stimuli, cytokines or PAMs, and then we tested the supernatants for ELISA. So just as an example of cytokines, we tested among a lot of other ones, interleukin-1 beta, and we can see that the secretion of interleukin-22 is similar in wild type and knockout mice. However, when we stimulate them with interleukin-18, we see that they mimic what we see in the colitis model. So the wild-type mice are able to upregulate this secretion. However, the knockout mice are not able to upregulate it. And the same result, we have seen them in TLR2 stimulation. So we have concluded that HIF-1α secretion of interleukin-22 is actually regulated by TLR2 and interleukin-18 stimulation. So, as ILC3s actually do not have TLR2, our hypothesis is that the TLR2 stimulation is actually done in other cells, other innate immune cells or epithelial cells. Those cells are the ones secreting interleukin-18 actually, and those are the ones that are actually stimulating ILC3 secretion of interleukin-22 through HIF-1α. So, to test that, we see that in infected mice, in colon of infected mice, interleukin-18 is actually upregulated. And furthermore, we have seen that when we stimulate colon explants with TLR2, interleukin-22 is upregulated. However, when we put the binding protein of interleukin-18, we see that interleukin-22 actually goes down. So we can further validate our hypothesis that it's through TLR2 interleukin-18 molecular pathway. So to finalize, it's just that the qPCR of isolated ILC3s, we can see that ILC3 stimulated with interleukin-18 actually upregulate transcriptionally the HIF. So it further validates our model and our molecular pathway. And moreover, in this stimulation with interleukin-18, we can see that the wild-type mice are able to upregulate the interleukin-22, whereas the knockout mice are not able to upregulate it, as we have been seen in the results of the colitis model, in vivo colitis model. So, as some of you may have noticed, I have not talked about the interleukin-17, which Most times it goes together with interleukin-22, it's studied together and share a lot of the molecular pathways. However, in this case, we have seen that they are differently regulated because HIF-1α does nothing. So we cannot see any difference in the steady state, we cannot see any difference during infection, and more importantly, in the testing of our molecular pathway, we cannot see any difference when stimulating with interleukin-18. So, as conclusions, HIF-1α is required for the induction of interleukin-22 by ILC3s after Citrobacter rodentium infection. Citrobacter rodentium infection regulates HIF-1α in colonic ILC3s in a transcriptional oxygen-independent way. Citrobacter rodentium induces the production of interleukin-18 in colon through TLR2, and TLR2-induced IL-18 is responsible for the production of interleukin-22 by ILC3s through HIF-1α. So thank you very much for the committee for selecting this short talk, and for my team in Madrid and our collaborators. And thank you very much for your attention.
Thank you.